the remainder theorem and the factor theorem. That's what we're talking about in this section. The goal, actually there's two goals. One is to long divide polynomials using synthetic division, which is a shortcut to long division. That's goal number one. Goal number two is to apply the remainder and factor theorems. And really, I suppose I should have capitalized these things because these are proper names here. I know it wouldn't matter much to you guys, but think about it this way. You guys are going to take calculus. Anytime you have a named theorem, you better know it for the test. In any calculus class, you're going to encounter something called the mean value theorem in your first semester calculus. You better know that theorem. Rolle's theorem, you better know that theorem. They're critical theorems for foundational calculus. Same thing with algebra. These are critical theorems for algebra, the remainder and factor theorems. We'll get to those in just a little while. So the first thing we need is maybe a more sophisticated way to write polynomials, a generic polynomial, than maybe you used in the past. So I'm going to use a lot of jargon here. Don't let it scare you. I'll relate it to other polynomials, examples of polynomials in just a second. So let's say you have a degree n polynomial, one variable. Then a generic way to write it would be using coefficients with subscripts. So the leading coefficient, which would be an, is well, that's just what we call it, an, and that would be the coefficient attached to the x to the n power, assuming a degree n polynomial. And if you write it in descending powers of x, the leading coefficient, an, will actually be in the lead, as will be the leading term, which is the first term. So an, x to the n, is also the first term, and the coefficient of that is the leading coefficient, or let me restate that. An x to the n could also be called the leading term, okay? An x to the n could be called the leading term, and an could be the lead coefficient. And it really will be in the lead if you write it in descending powers of x. The next one we could write as an subscript n minus 1, x to the n minus 1. The next one we could write, I bet you could predict, what would the subscript be? N minus 2, x to the n minus 2. By the way, this notation is not as scary since we covered sequences first, right? We use the same sort of notation with sequences and the binomial theorem and whatnot. And then let's do one more. Plus, what's the next one? A subscript n minus 3, x to the n minus 3. And then, okay, we could do this the rest of our lives, but it wouldn't be very productive. So let's go plus dot 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 plus. Eventually you get to a1 x to the 1 power. And then if it's non-zero, even if it is 0, we could name it a subscript 0. The constant term is called a0. Okay? So this would be the lead term. An is the lead coefficient. Again, if it's not written in descending powers of x, it won't be in the lead, will it? And a naught or a0 is the constant coefficient, some people call it. Okay. So some examples. What if you just have p of x equals c, where c is a constant? By the way, in the language from above, we could say p of x equals a naught. P of x equals just a constant. What would the degree of this polynomial be, by the way? If you don't have an x in there, you don't see x to the 1. You know, you guys are used to getting the degree by just looking at the highest power of x, right? Or the highest power of whatever the variable is. But if you don't see x to anything, if it's just a constant, there's only one way to define the degree when the polynomial is just a constant. What would the degree be? You can't call it 1 because like p of x equals 5x would be a degree 1 polynomial. It would be a linear polynomial, would be a degree 1 polynomial, right? So you'd have to call it degree, the only other choice is 0, right? So it would be a degree 0 polynomial would be a constant polynomial. You could think of it as x to the c times x to the 0 power, couldn't you? Kind of explains it. That would still be equal to c. Now here's the graph of it in red here. You can always replace p of x with y, or the function notation with y. Y equals c. When it's a constant, it just graphs to be a horizontal line, doesn't it? So that's probably the simplest example I could think of. The other ones you're familiar with, p of x equals mx plus b. Now, what would the notation be using our fancy looking generic polynomial up above? What's the degree here? Degree 1 polynomial, right? So if we wrote using the fancy notation from above, we could say p of x equals a1 x, or x to the 1, right? Plus a naught. So a1 in this case would be the slope, b would be the constant term. I'm just trying to get you used to the notation above. I'll probably never write it that way again. Usually we use mx plus b for the equation, or a linear function, or the equation of a line. So a degree 1 polynomial, it's a linear polynomial function, and it graphs to, it could graph to be a horizontal line if it's actually a constant, like above. It could be, the line could be graphed like that, slanted that way. In that case, m is bigger than 0. Or it could be slanted downward. In that case, m is less than 0. So you guys are really familiar with those kinds of graphs, so let's move on. How about p of x equals ax squared plus bx plus c? That would be your typical quadratic polynomial. In the subscript notation from above, what's the degree here? It's degree 2. So in the notation from above, n is 2. So we could say a2 x squared plus a1 x to the 1, or just x, plus a naught, using the language from above. Again, that's just trying to get you used to the subscript notation. I'll probably never write it that way. What is a quadratic polynomial graph to look like? It's either a smiley face, right, a parabola opening up, or a parabola opening down. We've already reviewed that a little bit this semester, right? And you might see a cubic also. How would you write a cubic? P of x equals, using the language from above, in a cubic polynomial, the degree would be 3. So what would the first term look like using the subscript notation for the coefficients? a3 x cubed. What would the next one look like? a2 x squared. What would the next one look like? a1 x to the 1. And then the last one? a0, right? And in practice, you'd get an example like this. P of x equals, I don't know, negative 5x cubed minus 4.2 x squared. Maybe a1 is 0, so maybe we'll leave that term off, plus 3. So you don't see an x to the 1 term. That just means its coefficient a1 is 0. Okay. So just that's the form of what you're up against in this section. By the way, polynomial functions are some of the most well-behaved functions in the world because they're created just using the operations of multiplication, division, subtraction, addition, and exponentiation, right? So you're not going to see in a polynomial function, you're not going to see like the square root of x. You're not going to see like an exponent that's a fraction. They're very nice formulas to work with. Okay, long division, everybody's favorite thing. Oh yeah. No, well, this is actually not what we're focusing on in this section. but you do need to be able to perform long division in certain circumstances. So let's review it. It'll be a quick review. To do the long division, remember this is what what do you call that thing? I call it the division garage. I don't know what the actual name is. I used to know probably, but I don't remember. I call this the division garage. Into the division garage, you put the bigger, nicer car, right? The Mercedes, the Bentley, I don't know, whatever you own. And that would be the numerator. What's that? Prius. The Prius, okay. And then in the driveway is out here. Here's the garage door. Everybody see the garage door right here? Okay, so in the driveway, you're going to put in, what's a really bad car?
Smart car.
A Prius. Used to be the Pinto, right? That was a all-time bad car. Oh, come on now. X minus 3 in the drive. So the denominator in the driveway, inside the garage, you put in the numerator. And then you ask yourself, what can I multiply? Okay, everybody look up. You got to see what I'm pointing at. What can I multiply like this x by to get the lead term x squared? X. And you're going to, the way I like to do it, I like to put the like term above the garage, on the roof of the garage, above the like term inside the garage. Not all books do it this way, but I like to organize it this way. So I'm going to put that x right above the 4x in the garage. And then this is really long division. It's just like the algorithm you use for numbers. So you're going to take that x and distribute it to the divisor, which is x minus 3. What do you get when you take x times x minus 3? So you distribute it to x minus 3, and you get x squared minus 3x. Then do you remember what you do with the number you get down here? You subtract it, right? But, okay, subtracting is the same as adding opposites, so I'm going to take the opposite of both operations down there, the opposite of both numbers, if you want to think of it that way, and then add. Same thing as subtraction, right? And the lead term should cancel. If you've done it right, the lead term should cancel. And then what do you get for 4x plus 3x? 7x.
Well, and sometimes these things can go on for a pretty long.
Right, but this one does not. So we bring down, what do we bring down now? Okay, but you have to include the operation, minus 8. So
What should we do there if it's one that does go on for a pretty
you do it until you get a remainder. Yeah. So now you start the process all over again. You see the 7x minus 8? You ask yourself, what can I multiply x by, that x right there, to get 7x? So, and you have to include the operation, so it's going to be plus 7, and you put that plus 7 right above the negative 8 inside the garage, the minus 8 in the garage. And then, again, you started the process all over, so you're going to distribute the 7 to the quantity x minus 3. So what do you get when you distribute 7 to the quantity x minus 3? 7x minus 21. And then what do you have to remember to do? Change the signs and add. You're really subtracting that entire bottom quantity, right? Okay, so what do you get? You get, okay, these guys cancel, and then you get 13, 21 minus 8. There's nothing left to bring down, right? So this guy's the remainder. So how do we write this thing? Yeah, we usually go the quotient, which is x plus 7, plus the remainder divided by the divisor. And what we're really saying is this original fraction is equal to x plus 7 plus 13 divided by x minus 3. That's what we're really saying. These guys are equivalent. Do you remember the check on division? This is important. The way you can check your answer is that this dividend, the thing you divide into, x squared plus 4x minus 8, should equal, anybody remember? You take the divisor times the quotient and add in just the remainder, just the 13. So it should be x minus 3, the divisor times the quotient, x plus 7, and then plus the 13, the remainder. So this is the dividend here, just to write out the check on division. This is the dividend. And this is the divisor times the quotient, q for quotient. No, there's no ambiguity there if I just use q, plus r for remainder. The dividend is the divisor times the quotient plus the remainder. And by the way, you can see real quick that this works, because if you multiply this out, you get x squared, FOIL it out, minus 3x plus 7x would be plus 4x. And then minus 21 plus the 13 does get you the minus 8 on the end here. So it does work. You do get the dividend, in other words. Now, it's really important to know that check on division, because it gives us a way to factor certain polynomials. If the remainder turns out to be 0, which was not the case here, but if the remainder turned out to be 0, then this guy is a factorization. The divisor times the quotient is a factorization of the dividend. And we're going to use that fact a lot, okay, in this chapter. That's only when r equals 0 you can say that. Does that make sense? So that's your quick review of long division. If the divisor is linear, what do I mean by that? Well, yeah, so like x minus 3 is your divisor here. If you set it equal to y, it will graph to be a straight line. But, I mean, really, if it's linear, it just means the power on the letter, the variable, right, is 1. If it's linear, there's a faster way to do this division. Somebody noticed a nice pattern, and you can do it without numbers. You can just use the coefficients. And it's called synthetic division. So that's what we're going to talk about next. Synthetic division works when the divisor is of the form x minus c. It's important you look at that. X minus c is the form that we kind of cling on to, where c is a constant. So we're going to, in this example, divide using synthetic division. I don't know why I wrote it so large. All right, so here's what you do. This is going to look weird. It's one of those things you have to do it 3 times and then you'll get it. So it'll look weird the first time I do it. What you're going to do is you're going to put c up in the corner. In this case, c is what? C equals 1. C is the thing you're subtracting from x. So c equals positive 1, okay? You're going to put c up in the corner. Like that. Off to the left. And then right across to the right of that 1, c in general, you're going to put the coefficients of your dividend, the thing you're dividing into. So what are the coefficients of the dividend? 1, -1, 2, and -3. Make sure nothing's missing. Your dividend has to be written in descending powers of the variable. And you can't have it skip from 3 to 2. Or I'm sorry, from 3 to 1. It's fine as is. I'll show you what to do later on if it's not written in order, or if not all the terms are there. But all the terms are there, so just write down those coefficients across from the 1 up in the corner. So 1, -1, 2, -3. And the synthetic division goes like this. Put your line there like I did. And you're going to bring down this first coefficient beneath the line. And then you're going to take the 1 up in the corner, this one right here, and multiply it times the number here. They both happen to be 1, which is why I'm circling them. And you're going to put the result, what happens when you multiply 1 times 1? You get 1. You're going to put the result right beneath the next coefficient from the dividend. And then you're going to add those two numbers together. You're going to add the -1 and the one in green that I just wrote down. So what do you get? 0. And then guess what? You start the process all over again. You're going to take the c up in the corner, which is 1, times the 0 that you got. What's 1 times 0? 0. And then you're going to add the 2 and the 0 together. 2. And then start the process all over again. What's 1 times 2? 2. And then -3 plus 2? -1. And that's your remainder, folks.
Could you do this with long division if you want?
You could do it, and you should get the same answer. Now, I haven't quite written down what the answer is. Okay, when you divide by a linear polynomial, the quotient goes down in degree from the dividend by 1. So we started out with a degree 3 dividend that we divided into. So our quotient should be degree 2. Look, it happened in the last problem. We started with a degree 2 that we divided into, and we ended up with a quotient that's degree 1. And that works when you're dividing by a linear factor. So what that means is the numbers that you have over here are the coefficients of the quotient. So that the quotient would be equal to, okay, this 1 would be 1 times x squared. This exponent is 1 number down from the dividend, the degree of the dividend that we started with. And then plus 0x, so this guy times the next power of x down, and then plus 2 would be the constant, which we would just write as x squared plus 2, right? And then the remainder is equal to -1. So if we wanted to rewrite this division problem, it's the same as the quotient, x squared plus 2, plus the remainder over the divisor, which is x minus 1. It's pretty quick. Yes? Yeah, so the numbers that we ended up with after finishing the synthetic division, these are the coefficients of the quotient that you get upon division, okay? And the quotient starts 1 degree down from where the dividend was. So we had an x cubed polynomial in your dividend, the thing we divided into. We're going to have an x squared polynomial for the quotient. In other words, we started out with a degree, we started out with a degree 3 dividend. That means we get a degree 2 quotient. And so you just write, okay, the numbers that we got, 1 would be the one that goes with x squared. 0, so this one right here is the one that goes with x squared. 0, this is the coefficient of x in your quotient, right? And this guy 2 is your constant term in your quotient. Is it okay now? Okay. Any other questions? We're going to do lots more of these, so don't worry. Yes? That's C. So this is C, which is this one right here. Yep. This guy, these are coefficients. This guy, and this guy, coefficients of the quotient.
Right, then under the line, that first one.
You just bring this guy down. Yeah. Let's do it. Let's do another example. I'll bet it'll become crystal clear. Like I said, it takes like 2-3 times, and then you need to do it yourself. And within 3 practice problems, you'll be done. You'll understand it, in other words. Okay, what's the issue with this division problem right here? It's not in order. So you might want to change that quotient right away so that the numerator is, okay, z to the 4th And then what's the next largest power of z you see? So plus z squared and then minus z plus 2. Write it in order. And then divided by z minus 2. Okay, so what goes up in the corner? What's c in this case? 2. Now you do have to be careful. In that numerator, it skips from z to the 4th to z squared. So what's missing is z cubed, right? So what's the coefficient of z cubed going to be? 0. You have to put that in when you line up the coefficients for that dividend. So what are those coefficients? 1, 0, is it 1 or negative 1? Negative 1 and 2. Okay, write down your line. Okay, bring down the 1. That's what we're doing. We're bringing down this 1. And then you start the process. 2 times 1, what's that? 2. And you put that right below the next coefficient over, the 0. So we should have 1, 0, 1, negative 1. Oh, you're right. Shame on me. I should be fired for that. Okay. Now that we have it right, okay, we bring down the 1. 2 times 1 is what? This 2, which we put right here, right? And then add everything together, what do we get? 2 plus 0 is 2. Start the process all over again. 2 times 2 is 4. Add them up, what do you get? 5. Start the process over again. 2 times 5 is 10. Add them up, what do you get? 2 times 9 is? Add them up, what do you get? 20. 20, that last number is your remainder. Oh, so by the way, never mind. I'll save it for this problem. 20 is the remainder. Now, we started out, what was the degree of the polynomial we started out with? Degree 4. So this quotient that we ended up with is going to be what? Degree 3. And these are your coefficients in order. So we're going to have 1 times, we better use z here, right? 1 times z cubed. 1 times z, normally I wouldn't put in the 1, but just to show you what I'm doing. So I took this 1 right here and put it right there. And then what's the next guy going to be? Going down, descending powers of z. 2 times z squared, then the next one? Plus 5z, and then the next one? Plus 9, and then the remainder is 20. Okay? If you want to rewrite this guy, the given quotient then is z cubed plus 2z squared plus 5z plus 9 plus 20 over what? Z minus 2. But sometimes you'll be asked to rewrite it like that. Sometimes you'll just be asked for the quotient and the remainder. And if you're just asked for the quotient and remainder, you're going to leave it kind of like this. Okay, now, Raquan, I think you had a question earlier I forgot to answer.
So for that first number that we put, what if it was z plus 2 instead?
Where at? What if it were z plus 2 down here?
Yeah.
Good question. We're going to answer that very shortly. But if it's of the form x minus c, or in this case z minus c, then you got to figure out what you're subtracting here. And you've done that before in different contexts. So you'd have to call c's negative 2, right? Because z plus 2 is the same as z minus a negative 2. So you just take the opposite of what you see. And you've done that before when finding like the vertex of a parabola and other situations. The center of a circle, right? Okay. So don't worry. We're going to do more of this synthetic division in just a minute. Okay, the remainder theorem. Looks strange, and then once you analyze it, it's like, oh, common sense. It comes from the check on division. So if r is the remainder when p of x is divided by x minus c, then R is equal to P of C. Now, what does that mean? You know what it means to have R, a number R as a remainder. So R stands for a number there. When you divide some polynomial, this is just a generic, a short way to write a generic polynomial. When you divide P of x by x minus c, the linear factor, we're saying that the number you get, R, is the polynomial evaluated at c, which sounds crazy. Why would that be true? I'll show you. Let's get there slowly, though. So in this example, let's let P of x equal x cubed minus 3x squared plus x plus 1, and we're going to divide. We're going to find the remainder when we divide by x plus 2. So this is kind of in answer to your question as well. So what do we put up in the corner? I guess we kind of already answered it. You must be psychic. Yeah, so c is actually negative 2. So that's what goes up in the corner, negative 2. And then what are the constants right next to it from the guy we're dividing into? We're dividing this guy by negative 2. So what are the constants? 1, negative 3, 1, and 1. Just do a quick mental check. Am I missing anything? The exponents go 3, 2, 1, 0 if you want to count x to the 0 times that 1, that constant factor of 1. So no, it goes down in descending orders, and I'm not missing anything, right? So you're good. So let's try the process. I'm going to have you guys tell me what the numbers are there. I'm just going to point. What goes underneath the line, underneath this 1 right here? 1. You pull down the 1, in other words. What goes right underneath the negative 3? Negative 2. What goes right underneath the negative 3 and the negative 2? So you add. What goes right underneath this 1? Can you see my cursor? Just barely. What goes underneath this 1 right here? 10. Okay. And then what goes underneath the 1 and the 10? 11, right? What do you do with the 11? And what do you put right here? Multiply, and you get negative 22. What do you get right here? You add, you get negative 21, and that is your remainder, right? Everybody with me? Again, try these on your own, and you'll have it in no time. It's the pattern just repeats itself over and over again. You're using your superpower of pattern recognition when you do synthetic division. Okay, so now we haven't talked about the remainder theorem yet, right? That's part B of this example. Part B, see if I can pull it up here. So part B says, find P of negative 2. Now we're just going to find it the old-fashioned way by plugging it in. So P of negative 2, what does it mean? Function notation, P of negative 2, what does that mean? In the function, polynomials are functions, by the way. I didn't prove that, but they do pass the vertical line test. We're going to talk about how to graph these things in the next section. You'll see that they pass the vertical line test then. So the polynomial function, P of x, what do you do to find P of negative 2? Plug it in, right? So you get negative 2 cubed minus 3 times negative 2 squared, right? I'm plugging in right here. Plus negative 2 plus 1. Whoops. Too far. Okay, and then what's negative 2 cubed? Negative 8. Okay, do the exponent first, you get positive 4, don't you? Times negative 3 minus 12. So there's minus 20, right? And then minus 2 gets you what? Minus 22 plus 1 gets you negative 21. Hey, guess what? The remainder is the same as P of negative 2. The remainder upon division by x plus 2, where c is negative 2, is P of c. That's the remainder theorem. Okay? Now, why would that be true? Is that like magic? Almost. No. What's the check on division say? I can more or less prove it to you with this one example. Let me shrink this down. Okay, what's the quotient here? It was a degree 3 polynomial we divided into. So these coefficients go with what quotient? X squared, 1x squared, right? Minus 5x plus 11. And we know the remainder is negative 21. So what's the check on division say? The check on division says that the guy you divided into, which is p of x, x cubed minus 3x squared plus x plus 1, that's your dividend, right? Is equal to what? The divisor times the quotient, okay? So what's the divisor? X plus 2. And the quotient? This guy, right? Plus the remainder. So we'll just go minus 21. So this guy right here is p of x. This x cubed minus 3x squared plus x plus 1. That is p of x. What happens when you plug in negative 2? Use this form from the check on division. What happens when you plug in negative 2 right there? You get 0. This whole thing is equal to, that's a big equal sign, 0, right? So what's left? Negative 21. That's when you plug in negative 2. This factor zeroes out, which makes this whole thing go away, and you're left with the remainder. The remainder theorem, once you look at it in terms of the check on division, it's pretty straightforward. Okay? Let me erase all that ugly stuff. All right. So definition, the number c is a 0 of the polynomial p of x if and only if, IFF, if and only if. Okay, if you can plug it in and you get the number 0. So I'm not saying c is equal to 0. C does not have to equal 0. It could. Doesn't have to equal 0, not necessarily. But what I am saying here is if you evaluate p of x at the number c, so symbolically you do that, you plug in c, then you get 0. And for real numbers, that's characteristic of x-intercepts, right? If you can plug in a number and get 0, then the point that you get from the input and the output, that's an x-intercept. So as long as c is a real number, c comma 0 is an x-intercept. So zeros and x-intercepts go together like peanut butter and jelly. Okay. So here's the other big theorem. We just talked about the remainder theorem. Here's the other one, the factor theorem. The number c is a 0 of p of x if and only if x minus c is a factor of p of x. That sounds confusing, so let's do an example. Let's find the zeros of p of x equals x squared minus x minus 6. So in other words, I want to find the numbers I can plug in to make this polynomial equal to 0. So what could I do? Yeah, just like you're finding x-intercepts, you would set the formula equal to 0. You could, but it'd be much easier to factor. So how does x squared minus x minus 6 factor? Got to be x and x, and you need two numbers whose product is negative 6, but they add to be negative 1. So I think throwing away the negative. One of them has to be negative, but 2 and 3 should do it, right? Which one has to be negative so that when you add them together, you get negative 1? So it's got to be x minus 3, x plus 2. Oh, okay. Well, you guys are in familiar territory. What do you do with both factors? Set them equal to 0 and solve. X equals negative 2 or x equals 3. Okay. So let me demonstrate then what these are the zeros, by the way. So this is the answer to the problem. These are the answers to the problem. But let me demonstrate what the factor theorem is saying with this example. The factor theorem is saying that if, and you know what, just to make it crystal clear, let me rewrite this factorization. X plus 2 could be thought of as x minus a negative 2. Would you buy that? This factor right here of x plus 2 can be rewritten as x minus a negative 2. Does everybody believe that? Okay. And then x minus 3 is good to go. So, and then if you solve this, either way, you get the same zeros. These are your zeros. So when you see that if and only if statement from the factor theorem, let's read it again to make sure it's in your head. The number c is a 0 of p of x if and only if x, the quantity x minus c, is a factor of p of x. It means you can read it both ways when you see that if and only if statement. So you can read it from left to right, but you can also read it from right to left using an if-then statement. So if x minus c is a factor of p of x, then the number c is a 0. You can read it backwards, in other words. And of course, you can read it as if the number c is a 0, then x minus c is a factor. So what we're really saying is, when you go through this process of solving by factoring, it's reversible. If you know that negative 2 and 3 are zeros, then that automatically means, of this polynomial, then that automatically means that x minus a negative 2 and x minus 3 are factors. So you have this one-to-one correspondence with the zeros and the corresponding factors. That's all we're saying. I mean, when you say it like that, it's kind of common sense. You already knew that, right? From all the work you've done with solving by factoring. But that's what the factor theorem says. So you give me a 0, I can come up with a corresponding factor. Give me a 0 from just a generic polynomial. Give me a 0. Think in terms of x-intercepts, a place where the graph crosses the x-axis. Give me a 0. 2. Well, we kind of just looked at that, except I think it was negative 2. Yeah. So what's the associated factor? X minus 2. Okay, so 2 is your 0. The factor that goes with it is x minus 2. Give me a negative factor. How about negative pi? Negative pi. What's the associated factor? X minus negative pi, which is really x plus pi. That's the factor theorem. Does that make sense? All right. So no big whoop, right? My alarm's going to go off in a couple minutes. Okay, in this example, let's let p of x equal 3x to the 4th plus 8x cubed plus 10x squared plus 2x minus 20. Show c equals negative 2 is a 0 of p of x. How could we do that? I got to look at part B to make sure. Yeah, okay. We could plug it in directly, right? And get 0. We could take p of negative 2 and get 0, right? But if you combine the things we've learned in this section, there's a quicker way. Couldn't we use synthetic division on this? Yeah. And if the remainder is 0, we know from the remainder theorem that that is p of negative 2. So the point of this example is we're going to use the remainder theorem, RT, remainder theorem, to find p of negative 2. It's quicker than plugging in directly. It is quicker than plugging in directly.
So that would be if you're dividing by x plus 2.
Well, c is the thing that goes up in the corner, so it doesn't matter because we're doing synthetic division here. C equals negative 2. Show c equals negative 2 is a zero of the polynomial. We're going to use the remainder theorem to find p of negative 2. So what are the coefficients that go across the top? Start with 3, 8, 10, 2, negative 20. Oh, am I concerned with anything happening out of order? Descending powers of x? I think we're good, right? But always have that in your mind. All right, you guys help me here. What goes beneath the 3? Beneath the line as well. 3. What goes right underneath the, what goes underneath the 8? Negative 6. Add them up. What do you get? 2. What goes underneath the 10? Negative 4. Add them up. What do you get? What goes underneath the 2? Negative 12. Add them up. What do you get? 10 or positive or negative? What goes underneath the negative 10? 20. By the way, if you don't get 0 on the end, you know you made a mistake, right? That's the beauty of these problems. You go back and you fix it. So what did we just show? The remainder theorem says that that's p of negative 2. We did it. Okay? Now part B, don't worry, we're almost done. Part B says factor p of x into a linear factor times a cubic factor. Wait a minute. This is the check on division, you guys. What's the quotient here? What's the quotient? So we went from a degree, what? So it was degree 4. So the quotient becomes 3x cubed. Help me out here. 3x cubed, this 3 right here, plus what? X squared plus what? Plus 6x minus 10. Okay. The check on division says what? That the original polynomial, I'm just going to call it p of x to save time, but this is the original polynomial. That p of x can be written as the divisor times the quotient plus the remainder, right? But the remainder is 0. So it gives you a way to factor it. What's the divisor? It would be x minus a negative 2, which would be x plus 2, right? That's where the x plus 2 comes in. Times the quotient. And then that's an answer to part B. I had to come back up here to look at what we had. But you take the divisor times the quotient plus the remainder is 0. Then you get what I just wrote down. Okay, so here's your divisor. And here's your quotient that we just got. And then plus the remainder, but the remainder is 0. We just showed that the remainder was 0 when you divide by x plus 2, that is, the remainder is 0. So that check on division gives you a way to factor the polynomial that you wouldn't have necessarily known otherwise.